Hello everyone, welcome to the video lecture of this course Finite Element Method. This is the continuation of the module One-Dimensional Problems. So in this module we have discussed the finite element modeling, then the finite element function. After that we have studied the derivation of the stiffness matrix, what is the concept of the shape function, how to use the formula of the shape function to solve different numericals. All these things we have discussed considering different numericals earlier. So there we have discussed the procedure to solve the displacement function, then the calculation of the stress, strain energy, then considering the different elements and nodal points. Considering all these things, we have discussed the procedure to solve different complicated problems of these one-dimensional bar elements. Today also, there are some more complicated problems regarding this procedure to solve the stiffness matrix, then the stress, strain, then the displacement function, all these things. So today also we will discuss two more complicated numericals based on the concept of the shape function and stiffness matrix. So let us start this lecture. So the first numerical states that we need to consider a paper steel plate of uniform thickness 25 mm, which is shown in the diagram. The Young's modulus of this plate is given as 2 into 10 to the power 5 Newton per millimeter square, and weight density is given as 0.82 into 10 to the power minus 4 Newton per millimeter cube. Now, in addition to its self weight, the plate is subjected to a point load of 100 Newton at its midpoint. So we need to calculate the following by modeling the plate with two finite elements. So what are the things we need to calculate here? First, we need to calculate the global force vector. Then we need to calculate the global stiffness matrix. Then displacements in each element. Then stresses in each element. And finally, the reaction force at the support. So these are the 5 different things that we need to calculate in this numerical. So there are some consideration in this diagram that we need to first take into assumption that in this problem the area of the element, it is varying at each cross section because it is a tapered shape. So if we consider this area variation, then in that case the problem will be lengthy and tedious. So in such cases, the given tapered bar, it is considered as a stepped bar, which is shown in this figure number 2. So this concept we have also discussed earlier in the theory part, that for the simplicity of the numerical, the tapered shape cross section, these are actually considered as a stepped bar. So here also that same thing we have implemented. So in this tapered shape bar, we have considered two different stepped bar or two different elements and three different nodes here. Now First we need to calculate the area at node 1. So at node 1 the area is width into thickness, so that means W into T. The width is given 150 millimeter and the thickness T is given 25 millimeter. So the area at node 1 it is 3750 millimeter square. Next, the area at node 2 A2, this is equals to W2 into T2. So this W2, its formula is actually W1 plus W3 by 2 multiplied by T2. So W1 and W2, these are actually given 150 and 75 millimeter. So we need to put the value of W1 and W3 here. After that, we can calculate the area at node 2, which is actually 2812.5 millimeter square. Next, we need to calculate the area at node 3. So the formula of this is W3 into T3. Now the width at node 3 it is given 75 and T3 is 25. So the area at node 3 this is 1875 millimeter square. So till now we have calculated the area at 3 different nodes. So the average area of element 1. So this is area at node 1 plus area at node 2 divided by 2. So this is the mean or average area of element 1. So finally we are getting the value of the average area of element 1. It is 3281.25 millimeter square. In this similar manner, we can calculate the average area of element 2, which is area at node 2 plus area at node 3 divided by 2. So finally we are getting the average area of element 2, it is 2343.75 millimeter square. So in this way, considering the tapered bar a stepped bar, we have calculated the area of the two different elements. Now the Young's modulus, it is given as 2 into 10 to the power 5 Newton per millimeter square. Weight density is given rho equals to 0.82 into 10 to the power minus 4 Newton per millimeter cube. The length of this bar it is given 300 millimeter. Point load P is given 100 Newton. So these are the 5 different things that we need to find in this numerical. So first we need to calculate the global force vector. Now the steel plate it is subjected to self weight, so that means we need to find the body force acting at the nodal points 1, 2 and 3. Now the body force vector F matrix, its formula is rho a L by 2 multiplied by the column matrix of 1, 1. So for element 1 and element 2, considering their nodes and the forces, we need to implement this formula of the body force vector. So for element 1 we are having two different nodes which are 1 and 2, so the body force vector it will be column matrix of f1 f2, so this is equals to rho 1 a1 average or a1 bar l1 by 2 multiplied by the column matrix of 1 1. So if we put the value of this rho a and l here, then finally we are getting the body force vector for element 1. This is 40.359, 40.359, its column matrix. This is our equation number 1. So in this similar manner, we need to calculate the force vector for the element 2. So corresponding to this element 2, we are having the nodes as 2 and 3. So that's why in case of this force vector equation, we need to write the column matrix of f2, f3. and on the right hand side of this equation we will write row 2 A2 L2 divided by 2 multiplied by the column matrix of 1 1. If we put the values of this row A and L here, then finally we are getting the equation number 2, which is the force vector equation for the element 2. Now we need to assemble this equation number 1 and 2. So that means in the left hand side of the equation we will be having a column matrix of F1, F2 and F3. So this is equals to a column matrix. That means we need to do the matrix summation or a matrix addition. So we are getting in the right hand side it is a column matrix of 40.3, 69.1 and 28.8. Now a point load of 100 Newton, it is acting at node 2. So that means corresponding to F2 vector we need to add 100 Newton. So finally the value of the global force vector we are getting is equation number 3, which is a column matrix of 40.359, 169.187 and 28.828. So this is our equation number 3 and the answer for the first part of this numerical. So we can see that for the first part of the numerical we had to find the value of the global force vector. So this is the third number equation, which is the answer for the first part of this numerical. Now we need to calculate the finite element equation for one-dimensional plate element. The general equation for the finite element equation, it is like the column matrix of F1 F2. This is equals to AE by L multiplied by symmetric matrix 1 minus 1 minus 1 1 multiplied by column matrix of U1 U2. So this finite element equation we need to apply for the two different elements here. Now for the element 1, which we can see in this diagram, this element 1 it is having the nodal displacements as U1 and U2 and its length is 300 millimeter. So if we apply the finite element equation here, so we will write A1 bar E divided by L1 multiplied by the symmetric matrix multiplied by the column matrix of U1 U2. So this is equals to force vector F1 F2. If we write the value of A1, then the Young's modulus and the length, then after several steps we are getting the equation 4. So this is the finite element equation for this element 1. Next for element 2, we need to apply this similar method of the finite element equation. So in the diagram you can see that corresponding to this element 2 we are having the two different nodal displacements, which are U2 and U3. So in this formula we will write A2 bar E by L2 multiplied by the symmetric matrix multiplied by the column matrix of U2 U3. So this is equals to a force vector of F2 F3. If we write the value of the area for this element 2, then we need to put the value of the Young's modulus and the length of this element. Then after 2 or 3 steps we will get the equation number 5, so which is the finite element equation for the element 2. Now we need to assemble this equation number 4 and 5. So which are the finite element equations for element number 1 and element number 2. Now if we assemble this equation number 4 and 5, then we are getting this representation as 2 into 10 to the power 5 multiplied by a 3 by 3 matrix, that is the stiffness matrix, multiplied by a column matrix of the nodal displacements, that is U1 U2 U3. So this is equals to a column matrix of the force vector, which is F1 F2 F3. So this is our equation number 6. we need to apply the boundary condition. So in case of this boundary condition, we can see that at node 1, as it is fixed, the displacement u1 it is 0. If we substitute the values of u1, f1, f2 and f3 in the question number 6, then we are getting this representation. That means we have entered the value of u1 as 0 and the value of the global force vector in the right hand side of the equation that we have already found out. Now in this above equation u1 this is 0, so that means we can neglect the first row and first column of the K matrix, which is the stiffness matrix here. So finally we are getting the reduced matrix here, and from that matrix if we do the matrix multiplication, then we are getting the equation numbers 7 and 8. So from these two equations 7 and 8, we can easily find the value of the nodal displacement at node 2. That means u2 equals to 9.053 into 10 to the power minus 5 millimeter. Now if we put the value of u2 in any of the equations of 7 and 8, then we can easily find the value of u3, which we are getting here is 10.898 into 10 to the power minus 5 millimeter. Okay, next we need to find the stress for the two different elements. The formula for the stress sigma, this is equals to E du dx. So for the element 1, we can write the formula sigma 1 this is equals to E to u2 minus u1 by L1. So this all the values of this Young's modulus, then the nodal displacements and the length of the element, these are known to us. So you can put all these values and finally we can calculate the value of stress, which we are getting as 0.060 Newton per millimeter square. So in this similar manner, we can calculate the value of the stress for the second element. So the formula of the stress for the second element, it will be sigma 2 equals to E into u3 minus u2 divided by L2. So again the value of the Young's modulus is given in this numerical, and the value of the nodal displacements, that is u3 and u2, and the length of the element, it is known to us. So finally we can calculate the value of the stress for this element 2, which we are getting is 0.0123 Newton per millimeter square. Next we need to calculate the reaction force, the support reactions. Now the formula of the reaction force, this R matrix, this is equals to the multiplication of stiffness matrix into the nodal displacement matrix minus the column matrix of the force vector. Now all the values are actually known to us and we have found out in this numerical. So we need to put the value of the stiffness matrix, then the value of the nodal displacements and the body force vectors. So now we need to do the matrix multiplication, and after several steps we will get the value of the support reactions. It is R1, R2 and R3 you can find from this equation of the reaction force. So finally we are getting the value of R1, this is minus 38.379 Newton, and R2 and R3, these are 0 Newton. Now we can also verify our result. So what is the concept here? That the reaction force, it is equivalent and opposite to the applied force. Now if we add all the reaction forces, then we are getting minus 238.379, and if we add the values of the applied forces, then we are getting it is 238.37 Newton. So that means the value of the reaction force, it is equal and opposite to the applied force. Finally, we have written all the results. That means for the first part, we have calculated the global force vector. Then for the second part, we have calculated the global stiffness matrix. Then for the third part, we have calculated all the three nodal displacements. For the fourth part, we have calculated the two stresses for the two elements. And for the last part, we have calculated the three different reaction forces. So this is the procedure to solve such type of complicated numericals, where we have considered the tapered bar as a stepped cross-sectional element. Let us discuss the second numerical. The question states that a rod subjected to an axial load P equals to 600 kN is applied, shown in the diagram. Divide the domain into two elements, and we need to determine the displacement at each node, then stresses in each element, and the reactions at each node point. Some data are given here that the area is 250 millimeter square, and the value of the Young's modulus, it is given 2 into 10 to the power 5 Newton per millimeter square. Now in this diagram, we have considered two elements, and corresponding to those two elements, we are having three different nodes. Now in such type of problem, we should first determine whether the contact occurs between the bar and the wall. And for that, we need to assume that the wall does not exist. Now the deformation at node, it is given delta L equals to PL by AE. So the formula of such deformation we have studied in strength of material earlier. If we put the value of this all four parameters, then we can calculate the deformation delta L at node 3. This is 1.8 millimeter. Now the gap between the wall and the node 3, this is 1.2 millimeter. So the contact occurs between the bar and the wall. So the displacement U3, this is equals to 1.2 millimeter. And the axial load P is given 600 kilonewton, area is given 250 millimeter square, and Young's modulus is given 2 into 10 to the power 5 Newton per millimeter square. First we need to find the displacement at each node, that means U1, U2 and U3 we need to calculate. Then we need to calculate stresses in each element, that means sigma 1 and sigma 2. And lastly we need to calculate the reactions at each node point, that means R1, R2 and R3. So first we need to use the finite element equation for the one-dimensional two-noded bar element. And the formula of the finite element equation is F column matrix of F1, F2. This is AE by L multiplied by asymmetric matrix, again, which is multiplied by the column matrix of U1, U2. So this is the formula of the finite element equation. Now corresponding to the two different elements and their nodes, we need to write the equation accordingly. So for the first element, you can write A1 E1 by L1, so multiplied by the symmetric matrix and multiplied by U1 U2, because this element 1, it is having the nodal displacements as U1 and U2. This is equals to the force vector, the column matrix of F1 F2. If we put all the values of the area, Young's modulus and the length, then finally after the matrix multiplication we are getting the equation number 1, which is the finite element equation for the element 1. Now in the similar manner we need to find the finite element equation for the element 2. So for that we can write the finite element equation as A2 E2 by L2 multiplied by the symmetric matrix, and here the nodal displacement matrix, it will be U2 and U3 because the nodes corresponding to this element 2, it is 2 and 3, and the forces, it will be F2 and F3. So after putting the values of the area, Young's modulus and length, we are getting the equation number 2 here. Now if we assemble these finite element equations 1 and 2, then we are getting the equation number 3, but the 3 by 3 matrix, it is the stiffness matrix K. Now we need to apply the boundary conditions here to find the values of the nodal displacement and the force vector. So at node 1, from the diagram we have seen that U1 this is equals to 0, and at node 3 U3 is 1.22 mm, which we have discussed at the start of this numerical. The point load P is given 600 into 10 cube Newton. It is acting at node 2 and self void, it is neglected. So F1 is 0, F2 is 600 into 10 cube Newton, and F3 is 0. So if we put the values of the nodal displacements and the forces here, then we can form this equation here, where we have entered the value of the nodal displacement U1, U3, and the values of the forces on the right hand side of this equation. Now from this equation we can do the matrix multiplication, and after 2 or 3 steps we are getting the value of the nodal displacement at point 2, that means U2 this is equals to 1.50 millimeter. Now to calculate the stress at the two different elements, we need to use this formula, that means sigma equals to E into du dx. So stress sigma 1, this is E into U2 minus E1 divided by L1. So putting all the values of these different parameters, we have calculated the value of stress sigma 1 for the element 1, it is coming as 2000 Newton per millimeter square. Is a tensile stress. Using this similar formula, we can calculate the stress for the element 2, which we are getting as E into U3 minus U2 divided by L2. And putting the values of the parameters, we are getting the value of the stress for the element 2, it is minus 400 Newton per millimeter square. So for the last part of the numerical, we need to calculate the reaction force. So the formula of the reaction force, it is the column matrix of the reaction force, this is equals to the stiffness matrix multiplied by the nodal displacement matrix minus the force vector matrix. So here all the values, that means for the K, U and F, for all these three matrices, the values are actually known to us. We have calculated for the first 4 different parts of the numerical. So we need to put all the values, and after that we need to perform some matrix calculation. So matrix summation, matrix multiplication, all these things we need to perform, and after that finally we will get the values of the reaction forces, that is R1 it is minus 500 kilonewton, R2 is 0, and R3 is minus 100 kilonewton. Now to validate or to verify our result, we need to use this concept, that is reaction force is equivalent and opposite to the applied force. So if we sum the values of the reaction forces, then we are getting as minus 600 kilonewton, and the value of the applied force also, it was 600 kilonewton actually. Okay, so this is the final result here, that is the nodal displacements. U1 we are getting as 0, U2 is 1.5 millimeter, and U3 is 1.2 millimeter, and the value of the stress for the element 1 is 2000 Newton per millimeter square, which is tensile in nature, and the sigma 2, that is the stress for element 2, it is minus 400 Newton per millimeter square, and it is compressive in nature. In the reaction force R1 it is 500 kilonewton, R2 is 0 kilonewton, and R3 is minus 100 kilonewton. And we have verified the values of the reaction forces with the concept that reaction force is equivalent and opposite to the applied force. So these are the two different numericals we have discussed today in this lecture, and we have seen how to solve the value of the global force vector, then global stiffness matrix, then the formula of the stress, then the formula of the reaction forces, how to validate and verify the reaction forces with the applied forces. All these things we have discussed in this lecture. So this is the end of this lecture.